Welcome back, everyone. I am so incredibly thrilled to have you here for this explainer, which is presented by Forge College. Now, if you're joining me today, it means you've successfully survived assembling the final comparative technical document. Yeah, that grueling capstone project where you had to consolidate all those heavy EVM and SVM architecture differences. So take a deep breath. You made it through.
I know. You might still be nursing a bit of a capstone hangover right now. Sorting through the dense weeds of blockchain architecture can definitely feel overwhelming. But I promise you, this explainer, it's going to be your light bulb moment. This is where all that heavy EVM to SVM transition theory finally clicks into place and becomes practical, actionable engineering logic.
Okay, so here's our engineering blueprint for today. We've got 1. Welcome to account models. 2. UTXOs vs account models. 3. The anatomy of an account. 4. The file system metaphor. 5. Practical state patterns. And 6. Designing for the SVM.
All right, Section 1. Welcome to account models, organizing principles.
Section 2. UTXOs versus account models, baseline paradigms.
Okay, let's dive into this. Before we even attempt to translate EVM-centric designs into Solana architectures, we need to understand that an account model isn't just some minor implementation detail. No way. It determines exactly where your data lives, who actually owns that data, and how transactions are allowed to change it. So let's look at the UTXO, or Unspent Transaction Output model. This is famously used by Bitcoin. Think of UTXO as kind of like physical cash. The ledger records discrete outputs that are consumed and produced by transactions, and each output is strictly immutable until it's completely consumed. Now contrast that with the account model, which is what we really care about today. Here, the ledger exposes an addressable state object. Instead of melting down and minting new coins, the fields inside this object can be read and updated directly. It's much like a standard bank account balance.
And why does this distinction actually matter for developers? Well, because concurrency, state provenance, and composability are not just buzzwords. This conceptual split absolutely dictates how your applications hold and mutate state across different chains. The UTXO model emphasizes stateless transactions composed of inputs and outputs, but the account model, it emphasizes mutable state that's tied directly to addressable entities.
Moving on to Section 3, Anatomy of an Account, Mapping EVM to SVM.
Now, what's really interesting about this is the massive contrast in what actually makes up an account here. Look at the EVM. We have an address, a balance in native currency, a nonce, and for contract accounts, a storage area that acts like a key value store indexed by 256-bit words. Honestly, it feels like infinite storage. But look at the SVM. An account has an owner program, a balance in LAMP ports, and, crucially, a fixed data byte array. It's an explicitly sized data container. Completely different vibe. Let's drill into how this actually impacts your code. In Ethereum, the magic word is implicit. EVM contracts conceptually own an unbounded key value store. When a transaction targets a contract, the code executes with direct access to this storage. Changes are simply applied to the global state trie atomically. You don't need a separate allocation step. The contract just implicitly owns its storage. Contrast that with Solana, where the magic word is absolutely explicit. In the SVM, programs do not implicitly carry storage around with them. Actually, scratch that. They don't carry any storage at all. Instead, they act on distinct, separate accounts. These accounts must be explicitly created, explicitly sized down to the actual byte, and explicitly paid for by covering rent or being rent exempt. Allocating memory is a very, very deliberate part of your application flow.
All right, Section 4, the file system metaphor, remapping your brain. So we're going to use an operating system metaphor here to help visualize this. Think of the blockchain runtime as a giant computer OS. The accounts are simply files on a hard drive, and the smart contracts are the active processes running on the machine, hopefully without crashing it, right?
In this metaphor, Ethereum is kind of like that overly trusting coworker who leaves their computer unlocked. A contract has a private directory it hoards and alters whenever it wants, without ever asking another process for permission. Solana, however, Solana is like a highly paranoid IT admin. A program can only act on files if it proves explicit ownership or if it's on a strict VIP access list. You have to request the file creation, size it properly, and prove you have right permissions for every single action. Section 5. Practical state patterns, architecture differences.
Okay, because the EVM implicitly owns storage, developers get really comfortable using unbounded dynamic mappings without pre-allocating byte sizes. It's easy. But over on Solana, because of that strict explicit ownership and fixed sizing, developers are forced to meticulously plan their allocations and ownership transitions upfront. If you want to change data size on Solana, you might literally have to create entirely new accounts or use some very careful data packing strategies.
Next up, let's look at concurrency and cost. In Ethereum, because contracts share that global state trie, the runtime pessimistically serializes state changes. It executes sequentially. But on Solana, because of those strict file permissions we just talked about, transaction instructions declare exactly which accounts they're going to read or write up front. And you know what this means? This allows the runtime to execute transactions touching disjoint accounts completely in parallel. It is a massive game changer for throughput. And for cost, instead of EVM's gas metering for computation, Solana makes you consider the rent-exempt balance proportional to the fixed space your account takes up.
So the crucial point is that these aren't just academic differences. The practical consequences mean when you port an app, you are facing a real architectural refactor. You'll likely need to split those large EVM mappings across multiple explicit Solana accounts. You'll have to design explicit interface boundaries because Solana programs pass accounts rather than making internal state calls. And drastically, you have to separate your code from your state. This means program upgrades require preserving ownership conventions and data layouts in a way Ethereum proxy patterns handle much differently.
Finally, Section 6, Designing for the SVM. Actionable takeaways.
Let's move to and see how this builds into a reliable developer workflow. Whenever you design state on Solana, you absolutely must respect the SVM account lifecycle. Step 1. Create the account and allocate the fixed space. Step 2. Initialize it by setting the correct program owner and initial data. Step 3. Use it by passing it explicitly into your transaction instructions. And Step 4. Close it when it's no longer needed so you can reclaim that precious rent Lamport balance. Make this your new checklist.
If you remember absolutely nothing else from this explainer today, I want you to burn this golden rule into your mind. Translate EVM implicit storage into Solana explicit accounts. Seriously, whenever you look at a Solidity smart contract and see a state variable, immediately ask yourself how that piece of data will be isolated, sized, and permissioned as a standalone file on Solana.
And that brilliantly illustrates the shift in mindset required to master cross-chain development. I want to leave you with this final, provocative architectural question to ponder as you start building. When you design your next decentralized application, who truly owns the data and exactly who must be included in the transaction to change it? The answer is going to define your entire system's architecture. Well, thank you so much for joining me for this explainer presented by Forge College. I highly encourage you to take these insights, apply them to your work, and visit forge.college for the next mapping exercise and to dive even deeper into a world of Web3 topics. See you next time.